Okay, I thought maybe this video might help you before you do your homework tonight. Because last week we only got to the second law. And so maybe I can quickly finish the second law and talk about the third law. So the second law says you have the sun at one of the two foci points. And the planet is orbiting it. Okay, so if you draw a line from the sun to the planet, and you stand here with a stopwatch, and you time a certain amount of time, and after that time, the planet gets to this point, and you could find this area that the planet sweeps out. Then you go over here with your stopwatch on the far end, when the planet's the furthest away, and you time for the same amount of time, and you get an area 2. And what you will find is that area 1 will equal area 2 as long as T1 equals T2. So we say that it's the planet sweeps out equal areas in equal periods of time. What that means, though, is the planet must be moving faster here when it's closer to the sun and slower here when it's further away. The point when it's closest to the sun is called the perihelon. There's an I in here, even though I didn't put it there. And the point where it's furthest away is called the aphelion. And the way you can remember it is that A stands for away, and the peri then is the close one. Now, if we were in class, I would say to you, and I did, I think, to one group, when do you think it's closest? And most people want to pick it being closest in summer. But our seasons have nothing to do with how far we are away from the sun, and everything to do with the tilt of our Earth, right? So if this is the sun, as our Earth goes around it, it's tilted either towards or away. And that's what causes the seasons, okay? And maybe I'll either do this in class the next time I see you, or okay, to explain that. So how far we are from the sun or how close we are from the sun doesn't determine our seasons. And that might seem weird, but remember the Earth's eccentricity. The eccentricity of the Earth's orbit is really tiny. And so the difference from when it's at perihelon to the sun and when it's at aphelion to the sun is really tiny. Actually, from where it is at perihelon to the sun, it's 147.5 million kilometers. And when it's at aphelion, it's 152.6 million kilometers. Now, this difference is not much. It's only 5.1 million. Now, that might be a lot. Like if you were going to give me $5.1 million, that would be a lot. But not when you're looking at how much we already have. And so the difference in the distance doesn't affect the seasons. When are we closest to the sun? We're closest to the sun on January 3rd. And when are we furthest from the sun? We're furthest from the sun on July 4th. And when I used to teach in the States, I used to say to my students, see, even the sun wants to be as far away as possible on your national holiday. Okay, just a way that you can remember it, July 4th. And again, in class, I will go over the seasons because I can't let you graduate without understanding the seasons. All right, so that's Kepler's second law. Really, though, it's the third law that leads us to the equations, that leads us to the important stuff, okay? So the back side of your sheet. And the third law says the average radius of a planet's orbit cubed. So remember, orbit of a planet is r. So r cubed of some planet, so we'll just put a p here. The average radius of the planet's orbit cubed over the planet's period of revolution squared. So period of revolution for the planet, so that's what the p is, squared, is equal to some constant. Okay, that doesn't sound that revolutionary. Just as a note, though, here, the period will always have to be in seconds, and the radius will always have to be in meters. And remember that when it's a radius of orbit, we use a capital R. In this law, it uses the word revolution. period of revolution as opposed to period of rotation. And hopefully you know the difference. Rotation is when you're spinning on your axis. Okay, so if this is the axis you spin around. Revolution is when you revolve around some other object. Okay, so this is the period of rotation and the radius of rotation. Okay, so what Kepler found was that if he looked at Mars and he took the radius of Mars cubed, radius of its orbit cubed, over the period of Mars squared, he got some number. Imagine. And so then he took the radius of Jupiter cubed, its rotation, of course, over its period of rotation, Jupiter, squared. And what he found was he got the same number. And then if we do it for the Earth around the Sun cubed, over the period of the Earth around the Sun squared, we get the same number again. Okay, so that's what this constant is. No matter which object, which planet you're looking at, when you cube its period of rotation, period of revolution, when you cube its radius of revolution over its period of revolution, you will get the same constant as long as they're all revolving around the same central body. So it'll be the same number for Mars, for Jupiter, for the Earth, for Venus, but it will not be the same if you do the Earth's moon's radius of revolution cubed over the period of revolution squared. You will get some number, but it will not be the same as the other ones because it's not revolving around the same object. But if you did it for the International Space Station's radius of rotation, of revolution, and period of revolution, it would be the same as the moon's because they are both going around the Earth space station. So as long as they're revolving around the same central body, r cubed over t squared will be the same. This we write as r cubed then over t squared, and the p there is just for planet, but it could be a moon, and so that's equal to some constant k. So this is your first equation. We don't often use it. We will use a bit more, r cubed 1 over t squared of 1, so the radius of revolution cubed over the period of revolution squared for one of the planets or one of the objects going around the same central body will be equal to r cubed of a second one over t squared of a second one. So this is a bit more useful. So this is Kepler's third law. But you know what? Kepler was only a mathematician. So he proved this, but he had no idea why. And it was Isaac Newton that had to come along to show the why. So Isaac Newton said, well, but just a sec, the Fc is equal to Fg. And so we know Fc is mv squared over r. And we know Fg is g m1 m2 over r squared. So one of these r's is going to cancel. And this m, this is the mass of the thing revolving. So it's going to cancel with this m over here, and we're going to get v squared is equal to gm over r, where this m is the mass of the central body, which in your notes I abbreviate it as CB. Excuse me, I have a tickle. Okay, but then Newton also said, hey, sorry, we know v is equal to 2 pi r over t. So let's fill this in here. And so it becomes 2 pi r over t squared is equal to g mass of the central body over r. If we square this, it becomes 4 pi squared r squared over t squared equals g mass of the central body over r. Take your r up, r cubed over t squared. That's Kepler's part. Bring your 4 pi down, g mass of the central body over 4 pi squared. So this is Kepler's piece. But look at what's on this side. G is always a constant. Mass of the central body will only change if it's not revolving around the same thing. This is a constant.